All right, recording is rolling. So it is Tuesday, January 10th. Yesterday we started the last AP topic that we hadn't covered yet. Unit 6 is simple harmonic motion, oscillation. Pendulum's a big deal. We did pendulum lab. We didn't quite finish that, so we've got a little bit more to do on that. We're going to knock it out today. And then I want to take the rest of the day to do a bunch of harmonic motion, oscillation, and also some waves demos with you guys. So do as many of those as I can today. Here's what I got planned next few days. I want to do a spring oscillation with you guys, which is on the same paper that you guys already have in front of you. Here's your pendulum lab. On the opposite side is like a spring oscillation. I want to try to do that tomorrow, and then do some textbook puzzles with you guys on Thursday. Let's see where we are by then. First of all, Friday to work with. Monday is MLK Day, and of course, you guys ate the classroom. How about by Tuesday? Okay, so let's finish this this pendulum lab. Okay, for this one, it's actually I'm going to switch my screen over, and I do have a convenient set of graphs going on. I know we were doing some graphing by hand yesterday, which is good practice. Oh, what's going on here? Is my screen frozen? Or is this not transferring? What? Okay, hold on. Timeout here. Timeout. Zoom recording. Okay, screen 2. All right, here we go. So, you guys remember we did time period versus mass. You guys have that one already. That's just a horizontal line showing no relationship. So, whatever the equation is that governs the motion of a pendulum has nothing to do with the mass of the bob, right? No, we are assuming that all the mass is in the bob. So, we've got a massless string or string with negligible mass, right? So, that's right. And it's the same story with the angle, the starting angle. If you pull it back to like 5, 10, 15, 20, 25 degrees, right? Same motion, right? Same time period, I should say, right? It might have a greater maximum velocity, right? Or you've got a question like that, right, at the bottom of the swing, but same time. Another thing that AP makes a point about is sometimes they want you to specify, like if you've got an FRQ question about this and you were like writing a paragraph, you might want to specify to only pull this like 15 degrees or something. I've seen that come up. I don't know, that might pick you up a point, right? And so like 15-degree angle or less, something like that, right? And then we moved on to this one. And now the textbook answer to this is time period is a function of length, right? Now, the longer the pendulum, the more time it takes to swing back and forth, but it should have been like a square root type relationship to it. Let's do this one from scratch because there's we got some more graphs to go with than involve this one. The volunteer, who wants to volunteer their data? All right, Stevie, what were your different lengths? 60,
46, and 34.
Okay, and what were the corresponding time periods?
16.3.
Okay, so I'm going to divide by 10 and call that 1.63. Okay.
Oh,
yeah, right. Yeah.
Okay. 1.51 and then 1.2.
Okay. Oh yeah. Look at that. See how? Okay, so you guys can imagine that part being part of a square root curve, right? You guys kind of see that, right? Now that's the last thing we did yesterday, and then the bell rang. Right. So here's where we're going to pick up. Right now, this next part, I want to make a big deal about this because this is a skill you definitely have to have for something like AP, is right, to be able to linearize something that's not originally linear. Okay. So far, we're suspecting this. We're suspecting that time period is proportional to the square root of length. Right? Maybe it's like a question, right? And we're going to test this. The way we can test this is if we do if we assume that this is true and we can go through a process with this and linearize the data, and it really actually does line up in a straight line, then that would sort of like confirm that it was the correct relationship versus like the cube root or the fourth root or something different. Okay, so there's 2 ways you can do this. One way is you could graph what's already there. You could say so instead of time period versus length, right, because that's a graph you already have, that's like a square root graph. Right? What if instead you graph time period versus the square root of the length, right? Okay. Now, if this is truly directly proportional, that should line up in a straight line, right? Maybe your points would be something kind of like this, right? Alternatively, right, and here's something skill you have to have for AP. Okay? Could you square both sides of this? Right? Notice that proportionality, think of it kind of like equals, but I'm leaving off part of the equation. There might be a little bit more to the equation. Okay. Could I square both sides and say time squared is proportional to the length, right? Just say the same thing. Say the same thing. All right, so then if you were to graph these, not set it back, you guys notice you have two blank graphs, right? You guys think these are the graphs, time squared versus length. Okay. Should be the same story. It should also line up in a straight line. Okay. And then you can interpret that slope and ooh, do you guys think the slope of this line has something to do with the gravity field of the planet? Right? Like you took pendulum to Mars or to a different planet, it would probably swim differently, right? Right. Now it might not be the gravity field exactly, but it has something to do with that, right? Just point some ideas here, right? Which, by the way, is the variable that we I forgot to mention yesterday. That could be a variable possibly with pendulum swinging, be like the strength of the gravity field. So we can't really test for that as an independent variable because we're all stuck in the same gravity field, right? All right, so back to here. All right, I've got Excel set up to automatically do this for us. Let's start with t squared versus L. How about that? Did I here? So yeah, so these two graphs on the right side of your lab page. Okay? One of those on the vertical axis, label it time period squared, and on the horizontal axis, label it length. Right? So that'd be time period squared in square seconds versus length in centimeters, I guess we got, right? Okay. And yeah, supposedly these points should line up in a straight line, like a direct relationship, and it looks like they pretty well did. Yeah, so there we go. That looks pretty good. Add trend line. Oh, look at that. There you go. All right, so pretty nice data right there, right? Okay. All right, so I got some graphing by hand practice yesterday. Right? Computer screen, same idea, right? Right, so can you guys scale the length up to, let's say, 80 centimeters as long as here? At time period squared goes up to like 3 square seconds. Okay. Put the dots about where they go. Direct relationship. Bam. You guys a little bit of time to do that. Okay, so scale and label your axes. Okay, just like we did yesterday. Only yesterday we had little tiny graphs, but so scale and label your axes. So length in centimeters is on the horizontal. Because 20, 40, 60, 80. And then time period squared in square seconds, right? So seconds squared, right, is on the vertical axis. It goes 0, 1, 2, 3. Okay, you guys got those points about where they go, and then everybody was here yesterday, I think, right? Nobody was absent, so everybody's got this page, right? You guys got that graph? Okay. All right, you guys ready for the next graph? All right, the last one. Okay, so last one, we're going to do the other manipulation that you could have done to get to the same outcome. Okay, instead of doing t squared versus L, you could have done t versus the square root of L. I just showed you guys on the paper. Okay, all right, so you guys ready for that graph? All right, here we go. Here's the last one. Okay. Oh, look at that. That's linear also, right? It's a little bit different perspective. How you interpret it, again, has something, the slope of that line has something to do with gravity field, but maybe from a little bit different point of view. Okay, but look at that. They all line up straight line, direct relationship. Okay. And so you guys are making your very last graph right now. We got time period in seconds is on the vertical axis. There's like 0, 1, 2. And the square root of the length and like square root of centimeters is on the horizontal axis. So 0, 2, 4, 6, 8, 10. So scale and label those axes. Put the dots about where they go. And we're looking at a direct relationship off of that data. All right, so well, let's check here. Right, you have the vertical axis labeled as time period in seconds. It goes like 0, 1, 2. You have the horizontal axis labeled as the square root of the length and square root of centimeters. Abstract unit. It goes 0, 2, 4, 6, 8, 10. the dots about where they go. Bam, direct relationship. Okay, you guys follow that? All right, so yeah, save this. You guys, that is some good data right there. All right, let's switch back over and finish this all the way because remember what we're aiming for is like what's a relationship that could govern the motion of this pendulum. Okay? And I had a setup for you guys that time period is proportional to, that's another way to say proportional to, is to do it that way. But okay. And so again, we're missing part of the like some for the full equation, but we have a proportionality, right? And very simply, it's just actually it's just right here. This is the answer. This is the answer to your lab right here. Okay. So very bottom, see the box says time is proportional. Oh, whoops. No, I guess it'd be this one actually. Oops. Okay, there we go. So where it says time is proportional to, right? You can say the square root of L. Okay. Right. So the square root of the length. So how about this? What could be like an AP application of this? Right? Suppose you had two pendulums and one pendulum was 4 times the length of the other pendulum. What would the ratio of the time periods be? 2 to 1, right? What if you had two pendulums and one was 1 meter long and the other was 9 meters long, 9 times the length? What would the ratio of those time periods be? 3 to 1, right? Right? You guys get that? All right. So you guys good there? All right. So hang on to this lab page, and then tomorrow I think I want to do the opposite side with you guys. Okay? That's the plan anyway. All right. Basic so far? So you guys have some new notes on your desk. Made these over the break. Okay. Now there's a few pages going on here, but there's only a part of this that you actually care about for AP. Okay, that's what's up, guys. But we're now getting into the part of the year where, well, you know, the classes are going to diverge a bit more in terms of the content. Okay. All right. So these first 6 slides I'm going to take you guys through have to do with harmonic motion. These you care about, except for the one with the hanger, right? The non-bob pendulum. In fact, if you want to scratch that out or something, it could possibly help you out with like one of the textbook problems. But AP is never going to ask about this, so you don't really care about the non-bob, but you care about the other 5. Okay, you guys with that? Okay. And then the next couple of pages notes are all related to waves, which AP used to ask about, but they don't anymore. So you're not going to be tested on any of this stuff. Right? Anything to do with waves, where it's a sort of property of a wave and everything after that. Right. So I'll take you guys through some demos and examples just so you're aware that, okay, this is kind of how this works, but then we're just gonna like move on from there. Okay. So focus more on AP stuff. Right. Okay. And then on the back of this whole packet, I have another lab lined up, which AP used to ask about, I'm not gonna ask about anymore. I might do a brief version of this with you guys maybe next week, but I don't know, we'll figure that out. Right. So let's go through these one by one. Right. So classic pendulum. All right, this is what you guys just did, and this is the full answer, right? So what's the relationship among all these variables? Right, you guys know this angle and this mass don't matter as long as here we got these assumptions. String is negligible mass, theta is small. Right? Right, the time period, so time to go back and forth. Okay, now you guys nailed this down exactly. Said time period is proportional to the square root of the length. Okay, here's the full equation. Okay, here's how the gravity field enters. All right, there's 2 pi thrown in there. Oh, so T equals 2 pi to the square root of L over G. That is also an equation on your AP equations. It's right down here. Okay, it's this one. Okay, so it's on your AP equations that you're allowed to use on the exam. Okay. Okay. Now there is here's for non-bob pendulum. I do this one because it's a more general case. You guys remember I for a single point mass is mr squared? You guys remember that? In this case, r would be L, so ml squared. Somebody else can't. Anyway, it reduces, it simplifies to this. Okay, if you think about that. Okay, but skipping past this one, just for fun. All right, oscillating block on a spring. I think it's gonna be tomorrow's lab. Now, there's 2 perspectives on labs, like 2 approaches. One is like maybe I call it like caveman labs, or I've heard it called inquiry labs, where you pretend you don't know anything about physics, but you have some basic measuring tools, you try to figure out everything from scratch. That's what we just did yesterday. Okay. Tomorrow I want to do like the other approach. Suppose you know this equation, right? You have it on your AP equation thing, and you have an FRQ that asks you to figure out like, oh, what's the spring constant based on the time period of oscillation? Right? And I'll show you guys a couple slides here how to get that. Right? So look, it's like the same structure as what we just did. You guys see if you put these 2 side by side, the same structure, right? Time period equals 2 pi to the square root of something. Okay. L or M is something you could very easily change out, right? Change the length of the pendulum, change the mass of the thing that's bobbing up and down the spring. Okay. This could be vertical or horizontal. I drew it vertical here, but it's the same thing. It doesn't matter the orientation of the thing. Okay. And then G is some kind of constant, right? G versus K, some kind of constant, right? Probably be a bit more difficult to change, right? Okay, so really similar structures. You guys see that? Right, you guys can figure that out. Okay. All right. All right, oscillating blocks on springs. Okay, so it's supposed to have one that's vertical. Let's put all the mass here on the spring, some spring constant K, right? It's like bobbing up and down, hanging from the ceiling. Okay. And put another one just going horizontal. And you know, I should have added this picture. It's like some kind of surface, a frictional surface. And that's how you normally get it. Right? You see some kind of surface down here, like a table, and they say negligible friction, right? And this one's just bobbing horizontally, right? Okay. Now, what's interesting is if you have a car going around a circular racetrack, just at constant speed. No, it's not constant velocity because it's changing direction, but constant speed, right? Speedometer is the same, right? You guys see how the horizontal location of this bob and the vertical location of this bob will always line up on the car. Actually, I think I have an animation of this. Let me put my I've been sharing my screen the whole time. Okay, that's all right. I'll make this work. All right, summation waves. All right, it's just gonna transfer over here. All right, there we go. All right, so kind of like that. And so there's the animation version of that. If you want to see that, switch back over here. All right, if you watch this video at home, oops, have my screen small for that. So there's classic pendulum. You don't care about not, you can just ignore this one if you like. Be an engineer or something. And then oscillating block on the screen, right? And here's what it looks like. Right? Right, now, what that means is, if you think back to like a trigonometry class, or we've done plenty of trigonometry here. You can represent the locations of these things with sine and cosine functions. You can do that, right? Sine and cosine, right? Which leads exactly to this right here, right? So oscillatory motion. Okay. So suppose here I got position versus time, velocity versus time, acceleration versus time. Hey, that's like the three classic kinematic sets of axes that, right? So whether you have something oscillating right and left, right, and say like what is its horizontal position, I think that's why they say a small angle, because the small angle that would line up really well with these type graphs. Okay? Or say like mass bobbing up and down, what is its location, its function time, like its height versus time, right? How fast it's going, and its acceleration, right? Okay. Now I know about half you guys are in calculus. You guys have taken derivatives of trig functions. You guys know that? Great. So what's the derivative of sine of t? Cosine of t, right? Right. And what's the derivative of cosine?
Negative sine.
Negative sine. Oh, you guys see that? You see that right here? Right. And then now this omega is called oh man, I'm drawing a blank. Harmonic frequency. Okay, remember it over the weekend, but it's 2 pi times the regular frequency, right? Anyway, right. So you guys see it's coming out like this, right? Now, if you're calculus, that's called the what rule? The chain rule, right? Chain rule, right? Right. So you guys know that, right? So every time you take a derivative, that's another rate of change, right? Right. Now, one more detail is, now the version of this that's on your AP equations, they actually say x is equal to, and then this capital A stands for amplitude. Okay, so like the amplitude, like how high it goes up. Okay. All right, on your AP equations, they actually have x is equal to a times cosine of, look at that, 2 pi f times t. Let me zoom in on that one. All right, where'd it go? Here it is. Right, now 2 pi f, right, where f is just the frequency. Now frequency is it's like 1 over the time period. So if there was a time period, I should write this stuff down too. Fill in some gaps here, right? Here, we'll give you guys some more context, and then I'll go into you guys what's going with this thing, right? So suppose like you have a pendulum swing back and forth, and the time period was like 3 seconds, right? Well, frequency and time period are reciprocals of each other. Okay, so f is frequency. Okay. Capital T, this week, next week, I'm kind of trying to reserve for a time period, not tension, but time period. Time period. Okay. All right. And time period, you guys know is measured in seconds, but frequency is measured in hertz, which is like 1 over seconds or cycles per second. Cycles per second. Right. Give you guys an example. Suppose you saw, here, how about the second hand on the clock? Tick, 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 tick. Could I call that 1 hertz
Good morning, Hawk. We have just been made aware by the text that there is a district-wide issue going on right now with the networking connecting and testing. They are troubleshooting it, but they're just asking if we pause school-wide on testing until they're able to address it. So wherever you're at, classroom talkers, if you just pause for a few minutes, Mr. Zaki should have further directions for us in just a few minutes. But there are some district-wide network issues that are being troubleshooted right now, so that we can resume testing in a few minutes. Thank you all for your cooperation.
That's supposed to sell like 2 beats per second. Like tick, 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 tick. Now you're going a little faster. Tick, 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 tick. Can I call it like 2 beats per second, 2 hertz? Okay. Supposed to sell 4 beats per second. Tick, 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 tick. It's probably pretty close, right? Okay. Do you guys think if you got up to like enough hertz at some point, your brain wouldn't be able to perceive the ticks? It might sound like a hum, like might sound like a frequency, right? Suppose you got up to 440 hertz. Musicians in here, what's that called? Is that called an A note, right? Like on a keyboard or guitar, right? Hit an A note. Well, that's one of them anyway. Okay. All right. So right, so now you got that. If you see omega in this context, this probably won't come up too much, but I don't know, I might show up here or there, right? That's 2 pi times the frequency. It has to do with like periodic motion and this sort of thing, right? So if I know what the frequency is in hertz, right, which is 1 over the time period, right? Dealt with a bunch of time period yesterday. Okay? Multiply by 2 pi, get the angular frequency. That's what I'm looking for. Angular frequency. Okay. Right, so all right, you guys got that? Okay. Right, so back to this right here. Got right now, why did they start with cosine instead of sine? I think that actually technically makes more sense than what I did, because you could start from a certain displacement, right? Like if you pull a block back on a spring, or you pull a block back on a pendulum, right? If you start with some displacement, then right, there's some impetus for it to have some kind of motion. Okay? You could really start with any of them. I started with sine just because I think it looks prettier in terms of the math, but it starts from 0 displacement. Just gave it a kick or something, right? You guys get the idea, right? Right? You start with sine or cosine, and it's just going to go into this. It's a 4-part pattern: sine, cosine, negative cosine, and then back to positive sine. Right? Right. You guys remember the rate change of acceleration? What's that called? It's called jerk. Right? You'll never be asked about that, but there you go. If you want to know the derivative. All right. Okay, this one here, right? This one is really, really important for AP, right? Because you are going to get questions about this on the AP exam. Make sure you can do this, right? Make sure you can start from either one of these formulas, right? Here's the answer to your lab, right? Here's the sort of similar one with the spring, right? And be able to, right, time squared versus like, I mean, this is what we just did sort of at the beginning of today, right? This one right here, okay? And this slope, remember I said it has something to do with the gravity field? Well, this is what it is exactly. Now, can you go from here to here? Right? This is a skill that you have to have, and it's the same idea for each of these. If you can do one, you can do the other one, right? Let's do some practice here. Let's go from this one to this one, right? Can you take something like this and linearize it like that? Right? So if you want to linearize something, you're looking for something like y equals mx, right? Where m refers to the slope. This is like an algebra set, right? Y equals mx, right? So how can I take some crazy looking equation and put it in this form? Y equals mx plus b sort of deal, right? Okay. So let's try this out. Time period is equal to 2 pi times the square root of the length of the pendulum divided by the gravity field. Okay. Suppose you know that's true, right? And somebody does some experiment and they get a table of data and say, here's a bunch of pendulum lengths, here's a bunch of time periods, and I wonder what planet we're on. It's just a crazy example, right? If you're an astronaut bouncing around different planets, like, wait, are we on Mars? I forget. I don't know. Break up the pendulum. We're going to find out. Okay. And you do a bunch of different lengths, and then you're going to turn this into a whole like graph, right? I mean, I guess you could use one length pendulum and at one point get the answer from that, but AP likes you to be able to make whole graphs out of this, right? So we're going to have lots of different pendulum lengths. We'll have short pendulums, we'll have long pendulums. We're going to somehow figure out what is gravity field. Now, you guys have done this a number of times before in this class, so this should be a skill that you should be solidifying at this point. I want that G to take the place of this, well, possibly the slope, right? There's a little bit different ways to go about this, okay? So some version of that. And the length and the time period, I want to sort of take the place of like X and Y, right? You can put them in either axis really, but right, just as long as you know what you're doing and how to interpret it. Okay? So, I don't like the square root. That's kind of in the way. Maybe it could square both sides, right? Could square both sides. Say time period squared equal, yeah, this isn't the only way to do it. There's probably like several different ways to do this, but this would be one way to do it, right? Boom, got rid of the square root, right? So that's out of the way, right? Okay. And actually right here, we're already at one of the answers. Because look at this, time period squared, but let's just take this G and shuffle it over here. 2 pi quantity squared over G times L. Hey, could this be Y equals MX? That'd be that, okay. Which is exactly what this is. Y equals MX, 2 pi squared over G. You see that? Boom, boom, boom. It's like 3 steps. You don't have to do it that way. You can do it other ways too. Let me show you guys another way you could do this. What if you want the slope to represent gravity field exactly? Right? Let me show you one way to do that. Okay. I can take the G, cross multiply it up here. Okay. Let T squared be the horizontal axis. So you do something like this. 2 pi quantity squared L is equal to G times T squared. Like that would be okay too, right? Is that the same thing? Okay. And you treat this as Y equals MX. Guess that? Where G would be the exact slope, right? Be able to do this, be able to do any of these. Okay. So then if I graphed 2 pi quantity squared L as the vertical axis, and I put the time period squared on the horizontal axis. So this could be in like, yeah, that's like meters. This could be in square seconds. Okay. Then I break out different pendulums. Okay. I'm swing back and forth. All the points should lie in a straight line, and the slope in this case is exactly what the gravity field of the planet. Okay. Okay. That right there comes from this right here. Okay. Okay. You guys can do that. Okay. Yeah, should be able to do this. Right. Should be able to break out just a blank piece of paper and a pencil and do this all from scratch yourself. Okay. Because you're gonna have to do that on the AP exam. Okay. All right. And then that is all the oscillations done. All right, then we get to waves. All right. So, all right. Here's what we do. I'm going to take the rest of the class today, which is just about 20 minutes anyway, and just do a bunch of waves demos with you guys. And then tomorrow we'll do lab stuff with oscillating motion. Here. I'll take you guys through these slides, and then I got some demos lined up on my computer too. Right. See how it turns out. Okay. And so this used to be on the AP exam. It's not anymore. But I want you guys to know a little bit about it. Right. So suppose you got some kind of wave, something that it is really has oscillating motion anyway. Right. If you go from crest to crest, that's called the wavelength. That's the shortest part that you can copy paste next to itself, where it could still complete the wave. Okay. You don't have to go crest to crest necessarily. You can go trough to trough. You can go from this node to this node, like one full S shape. Right. That can also copy paste next to itself. Right. Okay. Right. Oh, I told you guys this frequency is 1 over the time period. Right? Just told you that a few minutes ago. Right. Right. And here's the amplitude of the wave. Amplitude, capital A is amplitude. What's this deal about standing wave? Standing wave is like set up where these nodes don't actually move. Not every wave is a standing wave, but it could be. Okay? The microwave in your microwave oven, it's like a standing wave. Okay? You guys ever put something in the microwave oven? Maybe the turntable isn't working or something, and there's like hot spots and cold spots and whatever you pull out. Okay? You think that microwave is like maybe the cold spots is like where there's these nodes where it's like bouncing up and down, something like that. Right. Got some videos for you guys too. Right. All right, this right here is a really important wave equation. Speed equals wavelength times frequency. So this lambda represents wavelength. There it is right there. Lambda is wavelength. Right. F is frequency. 1 over the time period. V is speed. Right. So like, what's the speed of propagation? Okay. Different things take a wave property, right? So like light's a type of wave. The speed is like 3 times 10 to the 8 meters per second. Sound is a wave, right? Different kind of wave, pressure wave. It's about 340 meters per second. 1 atmosphere on Earth. Okay. Speaking of which, there's these 2 basic categories of waves. I don't know, some textbooks have like a third one or something, but these 2 ones really care about. And so transverse wave, where something's like bouncing up and down, where the propagation of energy is perpendicular to the motion of the wave, motion of the particles. Like the particles are just going up and down, the energy is propagating left or right. Okay. Versus longitudinal wave, where maybe you have like a bunch of particles. This is also called a pressure wave, right? When everything's like going in the same direction, so everything's like parallel to each other. Right? You guys can see that. Okay. What do you think sound is? Do you think sound is a transverse or a longitudinal wave? Sound. I said longitudinal wave is a pressure wave, right? Pressure wave. So would that be yeah, that would be longitudinal. Okay. So demo over here. Find that later. All right. The switch over here. Show you guys. All right. If you need to see the animation version of this, here's the animation version right here. All right. Oh, whoops. That's for earthquakes. It's the same idea there, right? You guys see right. So S waves and P waves, two different kinds of waves sent out by earthquakes. So transverse is on top, longitudinal is on bottom. Same idea there. All right. Over here. All right. We're doing all right, interference. So suppose you have a couple of wave pulses headed at each other, right?
Good morning, Hawk. Thank you so much for your patience during that delay. At this time, teachers, we are asking that anyone who can get into the test and is able to test, that we start testing with them. Any students in your room that are not able to get in, we ask you to send them to the courtyard. The techs are there with scanners. We'll scan the students and they will be on a makeup testing list for Tuesday due to the error code. So students, if yours are not working, we're going to have you come to the courtyard, look for Ms. Legate and Mr. Zaki, and we will get you set up for an assessment next Tuesday. Everybody else in your classroom that is able to test, please resume where you were with reading directions and beginning the testing process with all of those students. Thank you all for your assistance with it. Just to repeat, students who are able to get into their assessment, please allow the testing to begin and continue with that process. Any student that's not able to get in because of the district-wide browser issue, please send them to the courtyard. Mr. Zaki, Ms. Legate are waiting there for them. We'll assist and put them on a makeup list for the following Tuesday. Thank you all for your cooperation and patience. We really appreciate you.
All right. So suppose you have a couple of pulses at each other. You guys see as they cross that you could just add the amplitudes together. You guys see that? And also something that's interesting is that the pulses just cross through each other. See how they just like cross through each other? All right, so that's kind of cool, right? That's called constructive interference. Another version of this called destructive interference. Like what if one amplitude is positive and one's negative, right? The two pulses, right? Are still going to combine, are still going to pass through each other, right? Oh, look at that. Right, since they had the same amplitude, they washed out exactly while they were crossing, but yeah, they just went ahead and crossed right over each other. Also, you saw this one like reflect. You saw one of them like bounce off, and it bounces off actually upside down of how it was originally going. See that one more time. It's all slow motion, of course. Right, so looking at some destructive interference right there. Shoot, and the pulses just go ahead and cross through each other. All right. You know, I got some examples of standing waves here too. So let's take a look at this. All right, standing waves. Okay. See how the point where you're holding on the ends are not moving, so those would be called nodes, right? Yeah, you guys see like a node in the middle. If you went up and touched it in the middle, it wouldn't actually affect the motion, like I said. Right? Ooh, that right there. Right? How many wavelengths is that? How many wavelengths? That'd be one, right? One wavelength, right? Because that's one full S shape. Right? Oh, wait, if that's one, what is that right there? You say 1.5 wavelength, 1.5 wavelengths. Because here's 1.5, right? And then there's 2 full wavelengths. It's like 2 full S shapes, 2 full wavelengths. It's got some nodes and some antinodes, right? And the first, like start out with, would you call that like half of a wavelength? Right? It's only half of a full wavelength. Got that? All right. Let's go back over here. And since interference is a property of waves, you can use this to determine if something fundamentally a particle or fundamentally a wave. Like it was a debate for hundreds of years. What is light? Is light fundamentally particles or waves? And it turns out the answer is kind of both. But this was there was a famous experiment, this double slit experiment done to if you see some kind of interference pattern, that's usually an indication of some kind of wave-like property. Right? This is a fun lab. I might do a short version with you guys. Take like a tuning fork and strike it. There's certain places that in a pipe where it'll resonate. You guys know, like if you blow into a bottle, right, it'll like instead of a note, right? So if you take a pipe and put it in water, that's what this like light blue is, like water, right? And pull it up and down. At some point, it'll resonate like right? Except like these standing waves. And even though I drew transverse waves here, it's sometimes you can use transverse waves to represent longitudinal waves because it's really hard to like draw the dots and make it legible and you can kind of see what's going on. But sometimes you use one of these to represent one of these sort of deal. Okay, so same thing there. Right. Standing waves on a string. Right, here's the map of this. Right, so the length of the string I can call capital L. One full wavelength, remember, it's like one full S shape. Oh, and we just did the animation of this, right? So here, we just did that. I saw the animation. Okay. All right. What about musical instruments? Any stringed instrument? What's the physics of this? Okay. Well, the speed of the wave on the string is the square root of the tension in the string. Right. So like if you're tuning an instrument, right, you're changing the tension of the string, okay, divided by linear mass density. So the mass per unit length. Right. So got this nice formula, right? But what is the frequency of the note? Right? Because that's really what you care about, right? You plug a string, there's some note frequency, right? Well, I know the speed is wavelength times frequency. There's the frequency of the note right there. Right. And wavelength, well, if it just looks like this, it's 2 times the length of the string. Because we were just doing the animation version of that, right? Okay. So these all feed into each other. You can figure out, right? Okay, what's the relationship between the tension and the note frequency. Right. So if you're a musician, you might care more about this type of stuff. So like way back in the day, like thousands of years ago, people was, okay, well, what's the physics of music? Like how many different musical notes are there? What's the relationship between those? I think Pythagoras, I think it was the guy who was being on different pots, and I was like, oh, hey, these two sound good together. They like harmonize. I was trying to lay down the map of this. Do you guys know how many individual named notes there are before it cycles back to the next octave? Like chromatic scale, like all the notes, like all the sharps, and 12. Yeah, there's 12. There's 12, like 12 different notes. Right? Kind of a cultural thing. If you go to the Middle East, sometimes they have like 24 notes, but it's usually like some version of 12. Okay? So if you go from a root note to the octave, right? In terms of the physics, it's like doubling the frequency, okay? Doubling the frequency. Okay? And then all the notes in the middle, say like if you want to make a chord or something, well, these are notes that would make like a nice chord, like a major chord, right? But those what they look like, right? Now this is like something that like Pythagoras would be like more in line with like how Pythagoras would have thought of it, right? But modern musical instruments usually use what's called equal temperament, which is like works out really nice mathematically, but it's really close approximation of this, right? So it's like a logarithmic scale, like exponents. So if you start with a root note, like I told you guys, 440 hertz was one of the A notes, right? And you multiply by 2 to the power of something, right? Now n over 12, n is the number of half steps. And if there's like 12 different named notes, if you go up 12, you get to an octave above. 12 over 12 is 1. 2 to the power of 1 is 2. That'd be like doubling the frequency to get to the octave, right? Or if you went down, right, up or down. And what about like all in between? So like the fifth above is like 7. If you count up, it's like 7 half steps. So if you go 7 over 12, 2 to the power of that, right? And you can try this on a calculator. It's extremely close to a 3-to-2 ratio. So 2 to the power of 7 over 12 is, look at that, 1.498. Right. Now the major third is off a little bit, but it's like close enough. Yeah. Right, so there you go, equal temperament, right, which is an approximation of this. Right, Doppler effects. You guys ever stand out by the road and a car goes by and it's like, some kind of pitch shift going on, right? Okay. Like high to low. Now, of course, if you're in the car, you don't experience that or hear that, but like outside, the car goes by, there's some kind of pitch shift. Right? You guys hear the ice cream truck go by? Oh, hey, this is playing some nice song, like pitch shift. Right? It sounds all eerie. Right? Right, so here's the math of this. If you start with the note frequency, right? The frequency is like whatever note you're hearing, right? What's the source frequency versus what you're observing? Right? Now, if the car is parked, then everybody hears the same thing, because there's like no motion. So those two would be equal. Okay? Everybody, the observer and the source, they experience the same thing. But if you put this car in motion, okay, we got the speed of sound, which is about 340 meters per second, but it depends on the temperature and pressure exactly. Right. Plus or minus the speed of the observer, because this observer could be running back and forth. Hey, do you think if you're running towards the source, you would experience like a higher pitch? If you're running away, you experience like a lower pitch, right? And then the source itself could be moving, right? Same idea, right? Just moving towards probably a higher pitch and away is like a lower pitch, right? Yeah. I got a Doppler demo. Wait, where did I? Oh, here it is. It's here. All right. So I got a piezo. I'm gonna put this on a string, and this is all on a big old ball of yarn. So, safety going on here. Right. No, it's not complaining. All right. Yeah, it's working. Stuff that down there. All right. You guys hear that? Okay. Now if we put us around in a circle. You guys hear a pitch shift? Right. Now I have to take your word for it because I'm at the center of the circle, so I just hear a solid note. The kind of head towards you, it should be higher and then away is lower. There you go. All right. So Doppler demo right there. Stop. Ooh. Oh man. Ah. All right. Doppler. Hey, could the source be going faster than the very waves it's sending out? Ooh, can if it's sound, right? Is that called supersonic? Right? It's super greater than sonic sound, faster than sound. Right? You guys have ever heard like a Mach 2, Mach 3? Right? That's a ratio of how fast you're going compared to the speed of sound. Right? So if you're going twice the speed of sound, it's called Mach 2, like that. Right. Yeah, here we've got time for some demos here. Switch over. See what I got here. Where is? Oh, where'd it go? All right, here, okay. Supersonic. Yeah, you saw that jet fly overhead? You see it, see that like cone wave? See that cone wave? Hey, do you think if you knew the shape of that cone wave, it could tell you something about how fast that jet's going? I think so, right? I think so. Ooh, got some nice cone waves going on there. All right. Okay. Got a bunch more demos too. I might save some of these for another day, but switch back over here. Okay. And then how about how loud sound is? Right. So yeah, just goes that you guys, it's never going to be on the AP exam, but just be familiar with it. Loudness of sound is something that's like logarithmic. So if you look at like physical measurements of how intense a sound is, what's the pressure of a sound wave or the intensity in watts per square meter, the pressure in pascals or intensity in watts per square meter. Okay, you have crazy differences. So if you put it through this equation, there's two different perspectives on this, right? Sound pressure level, sound intensity level. Okay. You can get the number of decibels. So here's like something that's like 60 decibels. It's probably approximately how loud I'm talking right now. Maybe it's 60 decibels, right? But if you go from like 60 to 120, you're like, oh, hey, is that like twice as loud? Well, that's actually like many magnitudes, many orders of magnitude greater in terms of like the pressure and the intensity. Right? Like 120 decibels is like called the threshold of pain. Right? If you're getting like 20 pascals of pressure from a sound wave, right, on your ears, you have to like blow out your eardrums. Okay? And then 0 decibels doesn't necessarily mean zero sound at all. It's a tiny, tiny, tiny sound, which is like the threshold of hearing. Okay? So like that. All right, so there you go. There's sound intensity. All right. So had some fun with some demos there, got some oscillation, got a little bit of waves. Tomorrow I do a oscillating lab with you guys, and then yeah, textbook problems day after that. And I worked out. Okay. Okay, anybody got any questions so far? That sounds a good pause point today.